Hello. Familiar faces. That's great. So today we're going to talk about triangles. Apologies. So the assignment will be published today. Just finalizing it. So little bits and bobs. But it's available on the Miro board. So here is the link. So yep. And just to let me know, have you done similar triangles? Have you done congruent triangles? Congruent triangles. Okay, nice. So it might be easy for you, might be not. Let's see. Okay. So today we're going to do reasonably easy problems just to get in the habit of geometrical proofs. Okay, so let's get started. So here's the assignment. We talk about congruent triangles, talk about similar triangles. We're talking about medians, altitudes, and bisectors. Circumscribed circles and inscribed circles. Okay, so basically the standard stuff. So let's start easy. So what are congruent triangles? Congruent triangles are triangles which, by definition, have the same lengths and the same angles. So if angles are the same and all the lengths are the same, and there are three three ways to establish that two triangles are congruent. So we have the SAS congruence. If corresponding pair of sides of the angle enclosed and the angle enclosed between them. Are you familiar with these, by the way? Familiar with the SAS, SSS, AS, and SAA? What about you, Vishaka? Okay. So SAS congruence, just a quick reminder. So if you have two triangles, and we have a side, so this side is equal to this side is equal to this side, and an angle between them is equal, then the two triangles are congruent. Okay. The SSS congruence, if you have three sides of one triangle are equal to three sides of another triangle. So if this side is equal to this side is equal to this side, and this side is equal to this side, then the triangles are congruent. And then angle, angle, side. If we have angle, this angle is equal to this angle. This angle is equal to this angle. And the side, so for example, this side is equal to this side. Or it could be angle, angle, side. So we could have angle, 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 and side. So this is also congruent. So angle, angle, side. All right, so you can find these proofs here. And so congruent triangles. So this is here. This is pretty much the rules. So you should be familiar with them. Okay, so let's move on to problem 2. The median of a triangle splits the triangle into two triangles of equal perimeter. Show that the original triangle is isosceles. Okay, so we have a triangle. ABC. Let's say we have triangle ABC. Triangle ABC. Let's say that BM is a median. They say that the perimeter of triangle ABM is equal to the perimeter of the triangle CBM. Okay, interesting. So the perimeter is the same. So let's look at triangles ABM and triangle CBM. So by definition, so first, BM is the median. Therefore, AM is equal to MC. All right? So AM is equal to MC because BM is the median. 2. BM is the common side for triangles ABM and triangle CBM. It's like this sometimes is written as BM is equal to BM, but I mean, yeah, it is. Okay. CBM. And okay. So BM is a common side. And now the 3. Perimeter is perimeter 1 is equal to perimeter 2. But perimeter 1, so perimeter, that means AB plus BM plus MA is equal to CB plus BM plus MC. But we know that, well, BM is the same, so we cancel that out. MA is equal to MC, so we can cancel that out. And therefore, we have AB is equal to CB. So that means the triangles for triangle ABM is congruent to triangle CBM. Why? What is the reason? Which did we use? SAS, SSS, or AAS? SSS. What about the others? Do you understand? Do you understand what we're doing here? Okay. All right. Good. Because of SSS. Yes, we have the, side, side, side. Yes, so we've proved that the triangles are congruent, and if the triangles are congruent, that means that AB, therefore, you can use therefore AB is equal to BC. Therefore, triangle ABC is isosceles. That's it. That's what we needed to prove. Any questions here? Is it easy, medium, difficult, this problem? Okay. The angle bisector of a triangle is also its height. Show that the triangle is isosceles. It's somewhat similar problem. Do you think you can do this question without me? Would you? Okay. Try. All right, so we have triangle ABC. And suppose that BL is the bisector, is the angle bisector. BL is angle bisector. Okay. So if we draw BL, BL, the angle bisector. That means that this angle is equal to this angle. So first, 2. That means angle, well, that means angle ABL is equal to angle CBL. Now, for the angle bisector, it's also its height. So if it's a height, that means that this angle is 90 degrees. Well, and so is this. All right. So the angle is the same. Then this angle is the same as this. And BL is the common side. BL is the common side. And 3, triangle ALB is equal to the angle, sorry, CLB. The angle ALB equal to the angle CL. Yes, it's ASA. Oh, should we try it on Miro? We could actually try it on Miro. Why not? Well, I kind of already done it, but yes, it's ASA. ASA. So it's angle, side, angle. So therefore, for triangle ABL is congruent to triangle CBL, and the reason is ASA, angle, side, angle, because this side they have two angles and a side between them. And that means, so if the triangles are congruent, that means that 5AB is equal to BC because the triangles are congruent. That's yay. Perfect. Question 4. Are triangles congruent if two sides in an angle of one triangle are equal to two sides in an angle of another? SSA congruence, basically. Well, it does say that SSA is not a thing, but let's demonstrate why. Can you demonstrate why? Let me just give you. Can edit. Okay. So use the link. Can you show me why not? Hmm. You have two possible different triangles. That is true. Yes. You have two possible triangles that fulfill the SSA. I think what you've done wrong here, Luke, is that you've drawn a right angle triangle, which you shouldn't have. It's not supposed to be right. Yes, that's better. And the other one would be, yes, very good. Yeah, absolutely. So you have side, side. Yeah, and the same angle. So they have two equal sides. They're clearly two different triangles. This is equivalent to the ambiguous case of the sine rule. Same as the ambiguous case of the sine rule. All right. If two angles and a side of one triangle are equal to two angles and a side of another, well, clearly yes. Well, sort of. Hmm. Well, let me just give you a simple example. If you have two angles equal, that means the third angle is definitely equal. The third angle is equal. Now, two angles and a side of one triangle equal to two angles and a side of another. As long as they are corresponding. So only if corresponding sides is equal. If a corresponding side is equal. Because let's see, I'll give you an example. You have two triangles. Um, 3, 4, and 5. And another triangle. 5, 25 thirds. 8 and a third. And 4, 20 thirds. 6 and 2 thirds. These triangles are similar. They have the same angles. So this angle is equal to this angle. This angle is equal to this angle. And this angle is equal to this angle. But clearly, they're not congruent. But they do have the same side. It's not a corresponding side. They're similar, but not congruent. Right? Only if the corresponding side is equal. If the corresponding side is equal, then yes, it works. So if this side is equal to this side, for example. Because two angles guarantees that the third angle is the same, and that means the triangles are similar, and if one side is equal to the other side, then they are equal. Yes, if the order is the same, yes. If not corresponding. Bonding. Because the order but are those triangles really equal? Because the order they are in, or in the placement of the sides, different angles is different. I'm not sure what you mean. Oh, the triangle. Well, the way it is phrased here, okay, I should have used AS here. Yes, two angles is, yes. I shouldn't have used AS. So that's, it is usually, it is guaranteed. When we do AAS, the order is important. I see what you mean. Yeah. Okay. Show that the diagonals of a rhombus are perpendicular. Oh. A rhombus is a quadrilateral with 4 equal sides. Okay. So what can we do here? The diagonals of a rhombus. So this is the diagonal of a rhombus, and this one is the diagonal of a rhombus. And well, they do look perpendicular, surely. A, B, C, D. Let's call it E. So AC and BD are diagonals. And AB is equal to AD. AB is equal to AD. Therefore, triangle ABD is isosceles. That is isosceles. That means, therefore, angle ABE is equal to angle ADE. These angles are the same. Also, this side is equal to this side. And so then we can say AB is equal to BC. AD is equal to DC. And BD is a common. And therefore, that means that triangle ABD is congruent to triangle CBD. And that means that angle CBE is equal to angle ABE. So this angle is also the same. Okay. All right, all making sense so far? I haven't lost anyone. These two angles are the same. Now we look at triangle ABC. Triangle ABC is congruent to triangle CDA. And that is SSS congruency. And this is SSS congruency. In a similarly, all right. And also, we know that the triangle, these angles are the same because it's also AB is equal to BC. Therefore, triangle ABC is isosceles. That means that these angles are the same. But also because these triangles are congruent, ABC is congruent to CDA. That means that angle BCA is equal to angle DCA. So this angle is the same, and this angle is the same. So now looking at triangle, consider triangle ABE and triangle CBE. They are congruent because angle, side, angle, congruency. They have the corresponding angles, corresponding sides, and corresponding angles. Therefore, angle AEB is equal to angle CEB. Right? That means that this angle is equal to this angle. But if these two angles are the same, but angle AEB plus angle CEB equals 180. And if they're the same, angle AEB equal angle CEB equals 90 degrees. Therefore, AC is perpendicular to BD. Okay, now, there's no one unique way how to present this. There's no, and especially here, you could see that there's no, there are different ways you can prove the same thing. But as long as your structure, as you follow a logical sequence, then you're good to go. Okay. All right. So let's move on. Now we're talking about similarity. So this is example 4. It is from the assignment, but I just wanted to go through. The following diagram shows a trapezium ABCD, and AB is parallel to DC. The diagonals AC and BD meet at point E. The area of AEB is 49. The area of DEC is 25. What is the area of the trapezium? Okay, so let's use some notation. We're going to call this B1 as base 1. Let's call it B2 as in base 2. We're going to draw the height from E. Draw the height from E. And we're going to call it H1. And we're going to draw this height. And we're going to call it H2. Okay. So area of triangle ABE is equal to 1/2 base 1 H1. And then area of triangle DECED CDE is equal to 1/2 B2 H2. Okay. Now, DC is parallel to AB. Therefore, angle CDB and angle, well, we can say equal, CDB is equal to angle ABD. There's alternate internal angles. So this angle is equal to this angle. Similarly, angle DCA is equal to angle BAC for the same reason, alternate internal angles. So this angle is equal to this angle. The third angle, well, they are, and that means that triangle DCE is similar to triangle BAE, but by two angles, angle. Two angles are equal, that means the triangles are similar. And that means that the ratio of DC to AB is equal to the ratio of H2 to H1, and that's equal to the square root of 25 to 49. Because we know that the ratio of areas, A2 to, for similar triangles, or similar shapes, the ratio of the areas is k squared, where k is the, let's say, base 1 divided by base 2. Do you all understand what I'm talking about? Do I need to explain what k is? K is the coefficient of, well, it's the linear scale factor. Is the linear scale factor. And the ratio of areas is k squared. Therefore, 49. So the ratio of the sides is 5 to 7, because the ratio of areas is 25 to 49. Does that make sense? Okay. All right, so now we just need to calculate the area. Area of the trapezium. Area of the trapezium. Equal. Well, we know that the area of a trapezium is 1/2 sum of the bases, so B1 plus B2, multiplied by the height. And the height, it turns out, it's H1 plus H2. Now we open the brackets, it's 1/2 B1 H1 plus B1 H2 plus B2 H1 plus B2 H2. And we already know that H2 to H1 is 5/7, but also is B2 to B1. So it's going to be 1/2 open bracket B1 H1 plus 5/7 B1 H1 plus 5/7 B1 H1 plus 25/49 B1 H1. Because in each case I am replacing. So from here I say H2 is 5/7 B1 and H1, sorry, and B2 is 5/7 of B1. I'm using these in here and here. When I add these, it's going to 1/2 multiplied by B1 H1 multiplied by 1 plus 5/7 plus 5/7 plus 25/49, and that is 1/2 B1 H1 times 49 plus 35 plus 35 plus 25 divided by 49, which is 144 over 49 multiplied by 1/2 B1 H1. But 1/2 B1 H1 is the area of the bottom triangle. Well, already know that's 49. So that's equal to 144 over 49 times 49, which is 144 square centimeters. Any questions here? Show that the height of a right angle triangle splits the triangle. Show that the height of a right angle triangle drawn from the right angle splits the triangle into two similar triangles. Let's have a look. So we have a right angle triangle. And oh, thank you. Wherever that was. That is a height. So it is. So let's call it triangle A, B, C, D. Okay. We need to show that triangle ADC is similar to triangle CDB. Okay. Well, let's say that, yeah, this angle is X. So this is 90 minus X. Very good. And if this is 90 minus X, that is also 90 minus X. And that means triangle angle DAC is equal to angle DAC is equal to angle DCB. Angle DCA is equal to angle DBC. Therefore, triangle ADC is similar to triangle CDB, and this is angle similarity. So quite straightforward. I mean, there's nothing extraordinary here. But this is an incredibly powerful tool when dealing with right angle triangles. Let's have a look. Find the expression for AD and DB. This is another example from the assignment. Find the expression of AD and DB in terms of A, small b, and C, and hence prove the Pythagoras theorem. Okay, so AD. So we have a right angle triangle, ABC, and we've drawn a height from C to D. Okay. So we can say that triangle ACD is similar to triangle ABC by angle similarity. This is because angle A is common. Angle A is common for both, and each has a 90-degree angle. So by two angles, we have the 90-degree angle, and they both have angle A, whatever angle A is. And that means that CD that means that the ratio of AD to AC is equal to the ratio of AC to AB. We can substitute AD, so AD divided by AC, which is B, equal AC, which is B, divided by AB, which is C. No, we can't use Pythagoras theorem in part A. We need to prove Pythagoras theorem. It says hence prove the Pythagoras theorem, so it doesn't work like that. And from here, I can express the AD is equal to B squared over C. That's what we need, AD in terms of A, B, and C. Now, similarly, triangle BDC is similar to triangle, so BDC is similar to triangle CBA by angle similarity, as they share angle B. So this small triangle and the big one, they share the angle B, and they're both right-angled triangles. So therefore, by angle similarity, they are similar. Angle, they are similar. And that means that the ratio of BD to BC has to equal the ratio of BC to AB. Therefore, BD over BC, BC is A, is equal to BC, which is A, divided by AB, which is C. So from here, I can express that BD is equal to A squared over C. Nice. Finally, this is part A, done. Part B, hence prove the Pythagoras theorem. Well, we know that AD plus DB is equal to AB, correct? And now all we need to do is substitute. AD is B squared over C plus BD. BD is A squared over C. And AB, well, that's C. Multiply each side by C, and we get B squared plus A squared equals C squared. So multiplied by C. That is the Pythagoras theorem. Interesting. Wait. Interesting, as far as I'm concerned. Wow, that was quick, actually. Let's see if there's something. Okay, so just quickly, just angle bisector, you're probably familiar with. Perpendicular bisector of each side. The median and the altitude. So I hope you know the definitions. Okay. Okay. All right, so I found one more question. Let's see if we can do that. So we have a triangle. So problem 9. In triangle ABC. Okay, in triangle ABC, we draw heights BB1 and CC1. Find B1 C1 C1 if angle A is 60 and BC is 6 centimeters. Okay, so let's do this question quickly. So in triangle ABC, ABC. So this is a 60-degree angle. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . When you draw triangles, just be careful not to draw isosceles triangles, like I just did. Try to make them scalene. So this is A, B, C. Okay, and this angle is 60 degrees. And BC is 6 centimeters. Draw the heights. BB1 is a height. B1. And CC1. C1 is also a height. So this is a right angle triangle. This is a right angle triangle. We need to find B1, C1. B1, C1. Interesting. Okay, so what can we do here? Well, quite straightforward, actually. If this is 60, that means that this angle is 30. And because this is a right angle triangle. And if this is 90, that means this is also 30 degrees. Okay. 90. That means this is 60. And so is this. This is also 60. Let's just label this point. Let's call it K. Okay. So it has to be something to do with the triangles. Okay, so let's draw this side. B1, C1, the one that we're trying to, that's the one that we're looking for. Okay. So we can find these angles. So this is 120. So angle BKC is 120 degrees. And so is angle C1KB1 is 120 degrees. Interesting. Triangle C1BK is similar to triangle B1CK by angle. Does everyone see that? The triangle C1BK is similar to triangle B1CK by angle because it's 30, 60, 90. They're both 30, 60, 90 triangles. So I'm talking about this triangle and this triangle, 30, 60, 90. Nice. And that means that C1K, the ratio of C1K to B1K is equal to the ratio of BK to CK. Interesting. And that means, so consider triangle B1C1K and triangle BCK. Not BCK, CBK. CBK. We know that CK, the ratio of CK to, so from here we can write that CK to B1K is equal to BK to C1K. I'm just rearranging this. To write this. So CK to B1K is equal to BK to C1K. That means the two sides are in proportion. And the angle C1KB1 is equal to angle BKC, which is 120 degrees. Therefore, triangle BCK is similar to triangle C1B1K. So these two triangles are similar. So this triangle is similar to this one. And all we need is to find the coefficient of the linear scale factor. How can we do that? Well, let's see. So this side, BK, corresponds to this side. So the scale factor so equals to K, which we scale factor K is BK to C1K. But BK to C1K, if we consider the triangle, is equal to, because it's a 30, 60, 90 triangle. So this triangle is C1 K B K, because this is 30 degrees. So BK C1K. C1K to BK is equal to C1K to BK equals to sine 30 degrees, because it's the opposite divided by hypotenuse, right? So but sine 30 is, we know that it's equal to 1/2. All right, so that means that BK to C1K is 2. Ooh. I didn't anticipate that it's going to be so intricate. So the ratio of these two green sides is 2:1 because they are both part of a right angle triangle, which is 30, 60, 90. In a 30, 60, 90 angle, the side opposite to 30 degrees is half the hypotenuse. Therefore, scale factor, therefore, B1C1 to BC is equal to 1 over K, which is 1/2, and therefore B1C1 is 1/2 multiplied by BC, which is 1/2 times 6, which is 3 centimeters. Ta-da! So this is 3 centimeters. How well do you understand this last question? Did you manage to follow? Oh, very well. Good. So we managed to prove that the two triangles are similar. And once we have that, we can find the coefficient of proportionality, or the linear scale factor, which is equal to the sine of 30 degrees, which is quite cool. So yeah, this is like a nice one. This it's almost a pity that it's not in the assignment. All right, I'll finish here. Won't enjoy your evening, and I'll publish the assignment today so you can get so you can start it. And yeah, you're welcome. See you everyone.